Today we're going to talk about enclosure fire dynamics. We're going to use augmented reality to help us go through an enclosure fire. We're going to start from ignition, move through growth, talk a little bit about flashover, and then end with backdraft. So let's take a look at our little augmented reality image here. We have just a three-dimensional apartment set up. We have our fuels, and we already have a fire going in there. We'll talk about the fire in a second. So our fuels include this polyurethane foam couch and this chair. Let's take a three-dimensional tour of this, and what we have here is our we have a doorway. That doorway is going to become important later when we talk about backdraft. We have our ceiling. Ceiling is partially cut away just for visualization purposes, and so that gives you kind of a three-dimensional view of what we're going to be talking about. So let's start and let's talk about this fire first. Okay, you can see the fire is already going, so we have flames and we have our smoke rising from those flames. We know that ignition has occurred, so we know we had fuel, heat, and oxygen in the right proportion for combustion to occur, and it's continuing to occur because we have flames starting to propagate outward from that. So let's talk quickly about how smoke rises. We know that when we increase the temperature of a gas, that increase in temperature results in an increase in volume of the gases. That increase in volume and keeping the same mass results in a lower density. That density difference compared from the hot gases to the surrounding air results in lighter or buoyant forces to force these heated gases up. So that's how we get smoke flowing up, and this is that large yellow arrow that you see here on the image. And as that smoke rises out in the opening, it would just rise and eventually stratify out as it cools down. And since we have this in a structure, we have a ceiling. Well, that ceiling forces that flow to go underneath the ceiling. So we get these other yellow arrows that represent what's called a ceiling jet. So these ceiling jets is just the redirection of the flow, that thermal plume, underneath the ceiling. So now we're looking, and this flames have gotten larger. They've spread and started involving more fuels. As it spreads and more combustion is taking place, more and more smoke is developing and rising up in the thermal column. As that thermal column starts to interact with the walls, we start to see the redirection again of that ceiling jet, and those ceiling jets are sometimes referred to as wall jets, represented here by the curved arrows. And because the smoke will follow the path of least resistance, in this case the least resistance will be down into the compartment. So we can start seeing this distinct difference between this heated gases in the upper layer, what's termed the upper layer, that collection of smoke and heated gases near the ceiling, start to develop and descend from the ceiling. Now as that upper layer starts to form and descend from the ceiling, we start to see more and more smoke developing. And since our door in this compartment is closed, we start to see an increase in pressure, because if volume's increasing or expanding and has nowhere to go, it starts to increase the pressure on the compartment. Now it's not substantial if the door was open, because it would just flow out. But since the door is closed, we're starting to see a subtle difference in pressure change in the upper portions of the compartment. And what this means to us, though, is that as that ceiling layer starts to develop, or that upper layer starts to develop, we start to see involvement of additional fuels and more smoke developing. And if that smoke has nowhere to go, it's going to continue descending. As soon as that upper layer starts to descend over the top of our combustion area, our flaming combustion, then we start to see a decrease in combustion. That decrease in combustion will be because we have no oxygen to support that flame anymore. Here we have that upper layer descending, starting to interact with our combustion, our flaming region, and we can see a distinct disruption in our flaming combustion. And what we have, it's noted here as a circle around the flaming combustion region, is basically showing that because we are lacking oxygen, we are starting to see really poor combustion in that area. Poor combustion results in inefficient combustion products, obviously, and those include carbon monoxide, carbon dioxide, water, other things, whatever else is burning, such as hydrogen cyanide, and those types of things. As those start to develop and increase in the upper layer, we also have C's and H's, or hydrocarbons, that didn't burn because we lack the oxygen down in the flaming region, and if they don't burn, they release as a gas just the same as what carbon monoxide and CO2 are doing. So we're starting to fill the compartment with carbon monoxide, carbon dioxide, and our hydrocarbons, which will serve later as our fuel during the backdraft situation. Okay, since we have the upper layer forming and starting to develop, and it is increased in subtle pressure difference in the outside because of the higher temperatures, what we have when a door is open or a window is open, we get what's called a gravity current. That gravity current is the cooler air from outside rushes in to this compartment through that opening. It's going to rush in towards the bottom portion of that opening. So if it's a doorway, it's coming in on the floor. If it's a window, then it's going to be coming in through the bottom portion of the window. So what we have here, since we have a doorway, let's take a look at this. And as that door opens, we see heated gases and smoke starting to exit the compartment. And that exiting the compartment allows cool or colder air, which is called a gravity current, to come into the bottom portion of the opening. What we have in between those two moving fluids, the incoming air, fresh air, and the outgoing heated gases filled with hydrocarbons and carbon monoxide and those types of things, we get this mixing reaction noted here by the blue and red arrows. Between at the interface of the heated gases flowing out and the cooler gases flowing in, we start to see a mixing, and that mixing allows for flammable limits to start forming. As soon as we have flammable limits and those flammable limits reach an ignition source, that ignition source could be everything from heated metal, smoldering embers that flare back up with the presence of oxygen. Could be a whole bunch of different things. But as soon as it reaches that ignition source, now we're off to the races for a backdraft event. And basically that backdraft event will start usually near wherever the ignition source is and starts to propagate a flame through this suspended hydrocarbon fuel that's because of our inefficient combustion. What happens when the flammable limits are met from the incoming rush of air and the mixing of the hydrocarbons, or the C's and H's, that are suspended in the compartment due to inefficient combustion? Once you reach that flammable limit and you reach an ignition source somewhere in the compartment, you start a combustion reaction within the suspended fuel in the air. That's called a propagating flame. If you continue this fuel or the right mixture in front of that flame, you're going to continue the flaming combustion. And that flaming combustion is going to process through or propagate through this reaction. And as it's doing that, it's increasing in temperature, obviously, because it's combustion. When it increases in temperature, it increases in volume. That volume causes a pressure increase on the compartment as a whole. And because we have fluids that follow the path, well, all fluids follow the path of least resistance, these fluids will follow the path of least resistance, and since it's a closed compartment prior to the opening, when you open that opening will serve as the path of least resistance. So as that volume is increasing, the pressure is increasing, it's going to flow back out of that opening that was just made. So this door that we have that has been opened resulted in the air rushing in, as well as now the point of least resistance for the fluid to flow back out of. And because the flame is following behind it, you usually push out a tremendous amount of black, thick smoke filled with hydrocarbon fuel. Now it's mixing outside of the compartment with fresh oxygen, and the flame front is coming right behind it and serves as an ignition source and results in what we have here as a large fireball. And that is what's termed backdraft. Now, in this type of situation with a single compartment, you may not have a tremendous amount of overpressure, just really kind of a flash fire event outside, or this fireball outside of the compartment. However, if you have multiple compartments and turbulence is allowed to increase, the flame front propagation and your pressure to increase, what's going to result is you'll blow walls off of this compartment, or you'll even destroy an entire structure, because it cannot get to that path of least resistance, and it basically searches its way, not searches its way, but causes pressure increase everywhere, and the weakest part of the structure will give, and you result in an explosion. That explosion is termed a backdraft and has been known to kill a lot of firefighters.